Hi chemists, welcome back. We'll now be exploring some important ways that we can show chemical reactions. And before we dive into this, we do need to talk about a preliminary skill of writing dissociation equations and particle diagrams that describe these dissociation equations. So at the end of this video, you should be able to write dissociation equations for ionic compounds, illustrate the dissociation of an ionic compound using a particle model. Now, in order to talk about dissociation equations appropriately, we have to talk about what is happening when something dissolves. So remember, whenever a substance is indicated as aqueous or AQ, this means that the substance is dissolved in water. When ionic solids dissolve, their ions that make up the formula will dissociate or separate from each other. For an example, this is sodium chloride. So sodium chloride will start out as a solid, but when you add it to water, and then you see the H2O over the arrow, it's going to break up into its individual ions of sodium and chloride. This next example shows calcium nitrate dissociating, and I chose this one in particular because I wanted you to see that polyatomic ions will dissociate from their cations, but notice that the polyatomic ion stays intact. So notice nitrate, or NO3- is staying as one unit. It's not as if you make, for example, the nitride anion and the oxide anion. It's going to stay together. Now, once these ions dissociate or separate from each other, what's causing that to happen is basically the interaction with water, the attraction to water. So each ion is surrounded by water molecules in your solution. Now, it's worth talking about electrolytes and non-electrolytes. So ionic compounds that dissociate, they will conduct electricity. This is called an electrolyte. Non-electrolytes are solutions that do not conduct electricity. Now we have to talk about how we dissolve things in terms of a particle model. It really helps us to understand the dissolving process. So what we're going to do is we're going to observe the phenomenon. We're going to interact with a PhET simulation to observe the phenomenon to understand more about what's happening on the particle level when substances dissolve. We're going to use some guiding questions to help you understand more about this phenomenon. And then finally, you'll be expected to record your observations in the table provided on your guided note sheet. Here's the table that you'll be working with, and I've split this into 3 different categories. And these actually correspond to tabs in the PhET simulation. So we've got the macro tab, and we have some corresponding questions that you want to be able to answer. So it's my suggestion that you write your answers to these questions in that section of the table. Of course, you can include any other observations that you see in the simulation, but you definitely want to answer these questions because this will help you understand the phenomenon a little bit more. Now, we'll start first with the macro tab. So if I head over to my PhET simulation, I'll look at that first. So it looks like we're focusing on 2 substances. Let's answer this first 2 questions. So we've got salt and we've got sugar. And so with the salt, you can see it's in a little salt shaker. Here we've got the sugar. In terms of similarities, again, you probably just want to play with this a little bit. So like here's the salt, for example. And then if I look at sugar, notice that both of these are white solids. They're definitely white solids with each other. Now I'm going to start over again and I'm going to reset it. So I would say they're both white solids for sure. In terms of differences, it would be helpful to drag out the conductivity tester. So when you drag out the conductivity tester, you can actually move these if you want, but you do want to make sure both electrodes are in the solution. So what I'm going to do is I'm going to add some salt first. Right? And as I add salt and I continue to add it, hopefully you're starting to notice that the light bulb is starting to glow brighter, right? So you see those lines getting longer and longer. It looks like I'm out of salt. So let's see if we do the same thing with sugar, if the same thing will happen. Okay, so right away we're seeing that our sugar, no matter how much I put in here, I'm going to keep going. No matter how much I put in here, you can see the light bulb is not lighting up. But let's see if we need, oh, looks like we're out of sugar. Okay, so I would say one of the differences about these two substances is that the sugar does not conduct electricity, but salt does. And it looks like that kind of answers the last question about do all dissolved substances conduct electricity? So the answer is no. Okay, so that takes care of that first part. So now I'm going to go back to reset, and I'm going to go back to my micro tab. So now we want to look at the chemical formulas for salt and sugar, what each substance does when it's added to water, and I tell you to be specific, and what must be present for the solution to conduct electricity. So let's go back to our simulation here. And so if we go to the micro tab, okay, looks like now we actually have our chemical formulas. So here are the chemical formulas for these two things. And then we want to know, what does each substance do when you add it to water? Okay, so what I'm going to do is I'm going to first add the sodium chloride. So I'm going to just add it. Okay, so notice it looks like it was a solid. We knew in the previous tab that it was a solid, and it looks like now these particles are breaking apart from each other. And as I look right here, it looks like we've got sodium ions and chloride ions in equal amounts, which I think makes sense because sodium chloride is just one sodium ion to one chloride ion. And notice how these two ions have dissociated from each other. Now, if I remove the solute here, that'll take away the sodium chloride. Okay, so that's one thing. So it looks like if we were to summarize that, we would say that the sodium chloride, the ions break apart in solution. Now here's sucrose. So you want to think about what's the representative particle for sucrose. Well, it's a molecular compound, so that means that it's a molecule. So we've got a molecule here. Okay, so let's put some of that in here. Again, it's a solid. And then, okay, so if you notice, sucrose does break up, but it breaks up into molecules, right? Notice how these are not charged. There's no charges on these, okay? But it does essentially dissolve in water. So it looks like both of these substances break up in water, but the sodium chloride breaks up into ions, and sucrose breaks up into individual molecules. And then finally, okay, let's talk about this. So on the previous slide, or on this previous tab, we talked about how we saw conductivity when we added the salt to water, right? We saw that the light bulb glowed brighter, right? So hopefully you're saying to yourself that by adding sodium chloride, that is giving us a source of ions present in the solution. So it must be the ions that are responsible for the conductivity of electricity through this solution. So that's definitely something you're going to want to include in your observation. Okay, we got one more. So let's look at the water tab. So now it says, how do these substances behave similarly when added to water? How do the substances behave differently when added to water? What is the arrangement of water molecules around the positive ions and why? And what is the arrangement of water molecules around the negative ions and why? Okay, so let's focus on how they behave similarly and how they behave differently. So this is probably my favorite tab here. And so what I'm going to do is I'm going to just simply take note of my water molecules, right? These are H2O. And you know what I might do? I might show some partial charges here, right? Because you remember probably that water is a polar molecule. It's got a partial positive end and a partial negative end. So I'm going to put my sodium chloride in there first. And then just like we would expect, it looks like the ions will dissociate from each other. And I'm going to click pause for a second. So when I click pause, I'm just kind of taking note of the arrangement of these water molecules around the ions. And you can do this quite a few times if you want to. And if it kind of goes out of focus, like your sodium ions or your chloride ions are out of the way, you can of course reset it and do it again, which it looks like I lost some, so I'm going to do that again. Cool. Okay, and maybe I'll put my partial charges in there again. So one of the things that I'm noticing, and this kind of answers the last question, is that for our positive ions, it looks like the majority of the water molecules, the end that is kind of pointing towards the sodium ion, is the partial negative end. And hopefully you're saying to yourself, oh, that makes sense, because we know that opposites attract, right? And we're also kind of seeing something similar in that, again, opposites attract, because we've got our negative chloride ion attracting to that partial positive charge on the hydrogen atoms from the water molecule. So hopefully you're starting to recognize that opposites attract, and so that's what's ultimately kind of dissociating or pulling apart the crystal of the sodium chloride. So that answers the first part. So I'm going to reset this, and I'm going to look at sugar next. So when I look at sugar, one of the things that you can do is you can drop it in there and you can leave it as highlighted like that. If you click off of that, notice that sugar is made up of carbon, hydrogen, and oxygen. And so it kind of blends in with the water molecules. So that's why I kind of like to leave the highlight on there. But when you click play, notice that the sugar molecules still will separate, but the water molecules are kind of just like bumping around it. You don't really see any kind of like necessarily an alignment to these sugar molecules. And you can see almost that these sugar molecules, they don't separate as easily as maybe the ionic compound, the salt. So this might be something to also indicate in your table. So now what we're going to do is we're going to apply what we learned in this PhET simulation to illustrate a particle model that describes when sodium sulfide dissolves in water. So to do this, we want to first focus on some helpful things that can make it a little bit easier for us to draw these particle models. First thing is, I find writing the dissociation equation really helps. The second thing is, drawing the correct ratio of dissociated ions in the beaker is very, very important. And then third of all, orient those water molecules appropriately around each ion so that opposites attract. So we're trying to depict sodium sulfide. So what we're going to do is we're going to first write the dissociation equation. So we're going to show that the correct formula for sodium sulfide is Na2S, and that means it's going to break up into 2 sodium ions and 1 sulfide ion. Notice that I start out with solid, and I end up with 2 aqueous ions, and then I also have charges listed there as well. Then what I want to do is I want to actually show these ions in the beaker. So in my beaker, I should show that there are in fact 3 ions there, so that I have 2 sodium ions and 1 sulfide ion. The next thing I'm going to do is I want to make sure that I add those water molecules appropriately. So remember, water is a polar molecule. Therefore, there's a partial negative end and a partial positive end. So that means for us, we're going to want to orient the partial negative end pointing towards the positive ion. And we're going to want to orient the partial positive end towards the negative ion so that opposites attract. Now here's the thing. Not all ionic compounds will dissolve so well in water. And if you went on to study other chemistry classes, you would kind of learn as to why. But for our purposes right now, we want to talk about how would you depict, using a particle model, a substance that doesn't dissolve, or what we say is insoluble in water. So here's an example. How would the particle diagram differ if the ionic compound were insoluble? So if I gave you something like copper 2 hydroxide, for example, what we would expect to see is there would be copper 2 hydroxide solid sitting down at the bottom of the beaker. And you may say, Ms. Razz, why is it on the bottom? Well, we know typically that solids are more dense than liquids, so usually we would just have it sitting there on the bottom. Also notice that we have the ions alternating, because remember, these are made up of crystals of alternating positive and negative ions. And then also notice that these ions are not dissociated from each other. And that's intentional, because if you put a conductivity tester in the solid, it would not conduct electricity. In order for it to conduct electricity, you actually have to have the ions be mobile. They have to be able to move around. So this is how this particle diagram would look if we were describing an insoluble compound. So again, just to reiterate, copper 2 hydroxide does not dissolve well in water. It would be expected that the compound would not dissociate into ions and instead would form a solid at the bottom of the beaker. All right, that takes us to our very last slide. Thank you so much for watching. I hope this video was helpful.